So now let's develop the equations for the conservation of momentum. If you remember back to when we started talking about the Reynolds transport theorem, we said that if capital B, representing our extensive property, was momentum, then lowercase b, the intensive property, would be velocity. Or more formally, capital B is a vector, because momentum is a vector, is equal to m times velocity. And lowercase b, the intensive, is just equal to velocity. If we substitute these into the Reynolds transport theorem, we see that the time rate of change of the momentum of a system, and I'll write it like this, is equal to the rate of change of the momentum in the control volume plus the rate at which momentum enters and leaves the control volume integrated over the control surface. So we substitute in B and we get rho v dot n hat dA. This last term is a little bit confusing because we have two velocities in there. Remember, this is the rate at which the fluid is crossing the boundary, and the fluid crossing the boundary has a certain amount of momentum, which is this term here. And so when you integrate the momentum in any fluid particle times the rate at which it's crossing the control surface over that control surface, then you end up with the momentum that's carried in or out of the control surface, depending on the direction of the velocity. Here, this is pretty straightforward. We see that momentum shows up directly there, and the extensive property here on the left shows up here. Now, what use is this? Well, if you remember back from physics class, this fairly well-known equation, F equals ma, let's write it in vector form like that. Well, we see that ma is just equal to m times dv dt, and we can write, if the mass is constant for a system, which it is, then this, we can take the m inside the derivative, and we get d dt of mv hat. So knowing that, then, we know that the rate of change of momentum of a system is equal to the force acting on that system, or as we usually talk about, the sum of the forces acting on that system. We can make that direct substitution into the equation above, and we see the sum of the forces acting on a system is equal to all of the right-hand side of our Reynolds transport theorem. Now, in general, we'll have many kinds of forces acting on our control system. And these can include gravitational forces, viscous forces, pressure forces, and then other special forces, magnetic forces, and such, if the case arises. Now, when we derived the Reynolds transport theorem, if you remember, we started off with the system being coincident with the control volume, and then we developed the formula from that point. What this means is that for the consideration of the Reynolds transport theorem, the forces on the system can be translated to the forces on the control volume. So that means that we can calculate the forces on the control volume, and they end up on the left-hand side of this equation, and then we can calculate what's going on with the momentum within the control volume and the momentum crossing the control volume boundaries here. Let's work an example to demonstrate this. So let's say that we have the following. We have a support, or we have a, I don't know what you want to call this. We have a plate that is supported as follows. And we are going to shoot it with a jet of water like this. And we're going to say that the jet of water has a velocity of 15 I hat, where we've said that this is the x direction, and therefore that's where the I hat points, meters per second. And the nozzle area, so we're shooting this jet out of a nozzle, and the nozzle area is equal to 0.01 meters squared. Now we are going to assume that the water jet hits the plate and is diverted like this, such that the water leaving the plate is either going straight up or straight down. And our goal is to find the reaction force on the support. So find the force here, I'll call it Fr, on the support that this water causes. Now, because the water is moving in the x direction as it comes in and going out straight up and down, we're going to just write down the x component of the conservation of momentum equation. And we can see that if we do that, we write the sum of the forces in the x direction is equal to d dt of the integral in the control volume of rho, I'm going to use u because u is the x component of velocity that we're used to using, dv, plus the integral over the control surface of rho times u, and then here we end up with v vector dotted with n dA again. And the key here is that there are many different ways to draw a control volume, and in fact we'll do a couple different ways to draw a control volume, and some of them are better than others. If you do the analysis correctly, it doesn't matter what you choose for a control volume, as long as you keep track of all the forces and all of the momentum equations and such. You should always get the same answer if you do it right. But some of them, depending on how you choose it, will give more or less algebra or arithmetic to get to the correct answer. So what I'm going to do is I'm going to draw my first control volume like this. I'm going to call it 1 to differentiate from future calculations here in a minute. Let's see. So the next thing we do, so we've chosen a control volume, and now we need to go and analyze all of our terms in our conservation of momentum equation. We're going to consider steady flow. So the first term here on the right-hand side goes to 0. The only force in the x direction that's acting on this control volume is Fr here at the bottom. Now the calculation of the forces in the x direction is, in a way, it's trivial, but also a little bit tricky. So I'm going to walk through all of the possible considerations here. There are clearly no gravitational forces or body forces in the x direction. Gravity is working downward in this particular figure, and so that's that. There is Fr. This is acting on the this is acting right here at the edge of the control surface, and so it's acting as a to force the momentum towards the left. And there's a third one here that isn't apparent, but we have all along this left and right borders, we have atmospheric pressure pushing on our control volume. Even where the water is crossing the control volume, the pressure of the water crossing the control volume is atmospheric. And so we see that this acts all the way up the left and all the way up the right. And because we've drawn it in the way with equal sides on the left and right, the pressure force on the left and the pressure force on the right are going to identically cancel because they're both the same, atmospheric, and the areas are the same. So with that said, we can start writing down our terms here. Well, let's see, the sum of the forces in the x direction, we have Fr, but I've drawn it to the left here, so that's minus Fr. And that's going to be equal to the integral over the control surface of this term here. So we have three places where water is crossing the boundary. We have the jet as it enters here. We have the water coming down as it leaves here, and we have the water going out the top as it leaves here as well. Now, for regions 2 and 3, there's no u component of velocity. We specifically said that this velocity was going straight up or straight down. And so for regions 2 and 3, we get 0 out of this integral here. Even though there is a mass flow across the boundary, there is no momentum transfer across the boundary, no momentum in the x direction across the boundary because there's no x component of velocity across the boundary. So that leaves us with just the water that's entering at section 1. And if we consider this to be uniform velocity and uniform density, then the integral is fairly straightforward. We end up with density is rho, u, the speed, u is u. V dotted with n is u times I hat dotted with minus I hat because n is pointing outward to the left. So we get another minus u times the area. So that gives us minus rho u squared a, and when we plug in numbers, we get minus, the density is 1,000 kilograms per cubic meter, times, what was the velocity again, 15 meters per second squared, times 0.01 meters squared. And we go through and we do all the arithmetic, and we get minus 2250. We have, let's see, meters to the fourth on the top, and meters cubed on the bottom, so we get kilogram meters per second squared. And so we have a minus over here and a minus over here, so we rewrite F of R as 2,250 newtons. Because I've drawn F of R to the left, then F of R is positive in this diagram, and that's what it takes to resist the force of the water as it impinges upon the plate. Now, as I mentioned, we could have drawn a different control volume and come up with the same answer, and that's what we'll do here. Let's redraw our plate a little bit smaller. And we have our water jet, the same dimensions A and V. And again, it turns and it leaves the plate parallel to the plate. But this time we're going to draw our control volume like this. And we're going to say that it's right up against the plate here on the right-hand side. Now, we can rewrite our equations, and we ended up with the sum of the forces in the x direction was equal to ignoring the unsteady terms, the integral over the control surface of rho u v dotted with n hat dA. So it's clear that everything on the right here is going to evaluate to exactly the same. The area of the jet coming into our control surface, into our control volume, is just the same. The water leaving the control volume at the top and the bottom has no u component of velocity. So the right-hand side is just going to be equal to minus 2250 newtons again. The left-hand side is a little bit trickier. And as we alluded to in the previous one, where we had to deal with the atmospheric pressure, here it's actually important because we see in this one that on the left-hand side of our control volume, we have atmospheric pressure, which I'll call PA. But on the right-hand side, we don't have atmospheric pressure because we're right up against the plate in this particular case. And the plate will provide some reaction force, which I'll call R, which will act on the control volume as shown there. And I guess we need to define the area of the plate so that we can include the atmospheric pressure component. So on the left-hand side here, we end up with the sum of the forces in the x direction. Well, we have atmospheric pressure acting over the area of the plate, because the area of our control volume on the left is the same as the area of the control volume on the right, minus R, because R I've drawn pointing leftward here, is equal to minus 2,250 newtons. Or, right, okay. But now we have to consider, remember the question asked for the reaction force Fr at the support. So now, in a way, we have to draw another control volume. And we'll do this one in green. And now we consider a control volume that looks like this. Well, this isn't a fluid mechanics problem at all. This is, well, there's hydrostatics coming up, but this is a statics problem. And we see for the control volume in green here, we see that there's atmospheric pressure acting on the right side of this control volume like this. There's a force here, R, which is equal and opposite to the force that the plate is putting on the water to the left. And now we can sum up all of these forces from a solid mechanics point of view, if you will. And we see that R, which is to the right, minus Fr, which is to the left, minus A plate times the air pressure has to be equal to 0 because the plate and its support are not moving at all. And so we can rearrange this. We can take the A plate PA term and the R term to the right-hand side, and we see that PA times the area of the plate minus R is equal, so those go over here, A is positive, R is minus, is equal to minus Fr. And by substitution then, we see that minus Fr is equal to minus 2,250 newtons, or Fr, which is drawn to the left again, is equal to 2,250 newtons. So lo and behold, we do get the same answer. We just had to do a little bit more thinking about it and take a little more care in our bookkeeping because we drew our control volume in such a way that we had to explicitly take air pressure into account. Now this may seem kind of trivial, but if the question was to find what is the overall force acting at this boundary here, then it would have been very important to draw our control volume here as we did in red. so that we would get not only the force, not only the reaction force, but also the contribution due to the air pressure on the right-hand side.